Hi, everyone. I would like to thank the organizer to give me the chance here and to share my work here. I'm going to talk about Heegaard Floer homology and non-cuspidal curves. This video consists of two parts. In the first part, I give you like an overview of the background definition and our main result application. In the second part of the video, I just give the sketch of the proof of the main theorem. So this is a joint work with Maciej Brodik and Ian Zenke. And the notes is written based on the slides of Maciej when he gave the talk in the online seminar on Regensburg. Yeah, as we see in the title, we're going to see the non-cuspidal curves. So in this talk, we're going to study the curves in CP2. And by this, I mean a curve C, which can be regarded as the zero set of reduced polynomial in three variables. And there are some terminologies of this curve. The first one is the degree of this curve, which is regard as the degree of the polynomial f. Sorry, this f denotes this polynomial. And the degree of this curve C, we're understanding it as the geometric genus, which means it's the minimal genus of smooth closed surface sigma that projects onto C. So if the C is rational, we mean like the genus is zero, which means like we have a map maps to suggest this onto C. And once we have this polynomial, which gives us the curve C in CP2, we can talk about the singular point. The singular point means the point where the gradient of this function f equals to 0. For example, in this picture, we have 3 points, which are the singular points, which are denoted by 1 here, and 2, 3. So at each singular point, you can just consider the intersection of the intersection of this curve C. There's a very sufficiently small sphere S3 around the singular point with the center at the singular point Z. So this intersection will coordinate the link of singularities. It is a one-dimensional submanifold, and you're just obtain a link at this intersection. For example, the first place at the singular point Z, the intersection of the sphere and this curve C probably will just give you the T23 torus knot. And for the second one, you probably just not get a knot, but instead you get a link. This is a two-component half link at the second singularity. And at the third singularity point, you might just get another knot. Here, I just give the example of the torus knot T25. And based on the different number of components of the link you get at each singular point, you can define the branch. The number of the branch at each singular point is the number of the components of this link. For example, if you just get a knot, that's just really component 1 knot, and the number of branches is 1. And also we call such singular point as a cuspidal singular point. So whenever we say we have a cuspidal singular point at this complex curve C, we mean like it only has one branch, and we mean like at this link of singularity, it is really just an algebraic knot. In general, you could have more than one component. For example, if locally you can write the intersection at x to the power of p minus y to the power of q equals to 0, where pq is greater or equals to 2, then the number of the branches equals to the GCD of pq, and which actually gives you the link of singularity is the torus link TPQ. For example, here, this is p equals to 2, q equals to 3. This is p equals to 2, q equals to 2, T22. And this is p equals to 2 and q equals to 5. Great. So once we have this set up, we can ask the following questions involving the curve and also the topology data. The first question or the first problems people are interested in is called the realization problem, meaning like if we have a connection of link of singularities. So can we realize this link of singularities by some genus G curve? Yeah. So this is like fix the singularities, fix the link of singularities and try to find the curves with the genus G. And the second kind of question is the so-called classification problem, meaning like given the topological data, For example, you fix the genus of the curve and the degree of the curve, and then can we find all possible configuration of the singular points? The good way to describe the singular point is what kind of length of singularities can appear once you fix the genus and the degree. There are a lot of work towards this two directions. They're very big problems. People are interested in that. And in this talk, our main result is gives a partial obstructions to this kind of problem. And also, you can see from the title, the way we are trying to give the obstruction is from the Heegaard Floer homology. So I will leave the details of the Heegaard Floer homology in the second part. But in order to understand our main result, there's some important invariant. It's called the V function of a knot K inside S3. It's just a brief recall, like given a three manifold Y, you can just give a three manifold invariant from Heegaard Floer homology. And once you have this knot inside S3, you can give a filtration of the chain complex of the manifold S3. And from this package, you can extract some invariant called the V function of the knot. This is a knot invariant. And the way we describe our main result is using this V function or this V invariant for the knot. The main theorem given is we show like, let's C be a degree D curve with genus G and H double points, and also one cuspidal singular point Z. So we get the following restrictions. For any K starting from 1 to D minus 2, we get the mean of the RKD plus 1 minus 2G plus G is greater or equals to 1/2 of K plus 1 times K plus 2. Here, this R is defined as following. So R is defined as, this is a function, is defined a function over Z. So you define the way as RG plus J equals to Vj of K plus J, where Vj of K is the V function of the knot K inside S3. This is our singular point. This is the link of the singularity from the knot from the point Z. Sorry, and then this R is a function determined by the V function. So it is also a knot invariant, just determined by the link of singularity K. So the way we describe our obstruction is using this R function, which is defined in terms of the V. The second obstruction is the maximum of this R function valued at KD plus 1 minus 2J minus H plus J smaller or equals to 1/2 K plus 1, K plus 2 plus G. And here G is the genus. D is the degree, and the K rounds all the number from 1 to D minus 2, and J is also rounds from either from 0 to J or 0 to G plus H, sorry, and it takes mean or maximal over all the possible values of J. So though this is a little abstract, and it maybe make more sense if we talk about the applications later. But one thing I just want to point out is like, though our main theorem says your curve C only has one cuspidal singular point Z, but this theorem can be generalized, meaning like we can consider the curve with the singular point Z1, Z2, Z3, Z4, etc. Zn, and then your R function is kind of can still define for the connect sum of all these knot K, and you can still get the similar obstructions as we had here. But I won't give the formula here because we probably won't talk about the application for more than one cuspidal curve for more than one singular points. The second result is now we have the complex curve C. It has degree D and also genus G, but now we have L negative double points. So in the last theorem, it's positive double points, and here we replace it by negative double points. And also we assume that it has one cuspidal singular point Z. This gives you the knot, the link of the singularity K, and we assume, because it's a cuspidal singular point, so it corresponds to one component knot, and we just assume it is the knot K. And this R function is also defined in terms of the V function of this K, so you can just regard it as a knot invariant regarding to this singular point. So for the second obstructions we had is also looks very similar to the first obstructions in the last theorem. We consider the mean, we consider the maximal over all the possible values of J starting from 0 to G or starting from 0 to G plus L. And here K is also from 1 to 2, etc., D minus 2. And D is the degree. L is the number of negative double points. On the right-hand side, it only depends on K at first inequality, and the second equality, the right-hand side also involves the genus and the number of negative double points. There is a very big difference between these two theorems. In the first theorem, we say like we can generalize the result to arbitrary many cuspidal singular points. However, in the second theorem, it only works currently for only one cuspidal singular point. So it does not work if we have more than one cuspidal singular point. The reason is because we don't have a good description for finding the R value on the left-hand side of these inequalities. Yeah, it's very abstract just to see this restriction. So we just to see one applications people are interested in by using this these obstructions. One thing is like we would like to compare the double points and the genus. So the question is saying like if we have a complex curve C, and we assume like it has a singular point Z. So you can ask 2 points, whether you can find a curve C has genus 1 with this singular point Z, that's the first kind of situation. Or you can ask ourselves like, can we find a curve with genus 0, but we have a single positive or negative double points plus the singular point Z. I just write these 2 cases. The first case is a curve C that has a singular point Z plus genus 1. Or the second case is find the curve C. Still you have the singular point Z. But now you just required has genus 0 and plus a positive or negative double points. This questions of the comparison between these 2 situations is kind of saying like whether you can trade the genus by a positive or negative double points. So surely you can also ask yourself a more general scenario is like, can we find a curve C with more than one genus? You can just say genus, arbitrary genus G curve, and then maybe just replace 1 or 2 by some positive or negative double points. This is the general scenario. So an abstract comparison for this possible obstructions is the following. In either case, in its 3 case, like genus 1 or positive double points or negative double points, they all need to satisfy this following restriction. So recall like this R is a function over Z to Z. And it's just a not invariant. You can just regard it as a not invariant. And this not is really just the singularity, the link of singularity. So no matter you have genus 1, positive double point, negative double points, they all need to satisfy like R valued at KD minus 1 is inside K minus 1 or K, and the KD plus 1 is valued inside K and K plus 1. Here, small k is valued as 1, 2, 3, 4, D minus 2, as you can see from the theorem. And this big K is defined as 1/2 of small k plus 1 times K plus 2. So this does not tell us anything because all the 3 situations needs to satisfy this restriction, so it does not distinguish the 3 cases. However, if our curve C has a positive double points, it needs to satisfy this following inequality, that the R function evaluate at the point KD, I just read small k, small KD is smaller or equals to the big K. Big K is still defined in this way, and small k is defined as all possible values from 1 to D minus 2. So if you have 1 positive double points, you have an extra inequality you need to satisfy. And this obstruction actually can help us to distinguish the genus and the positive double points. The next seems is like if our curve C has a negative double points, then you need to satisfy this inequality of R if value at the KD is greater or equals to K. And so here is still small k, and this is the big K. So this extra two inequalities gives a way to distinguish genus and positive double points and negative double points. And actually it gives a hope to give obstructions of trading genus for double points. I'll give one very explicit examples for this situation. So there is a proposition given by Orekov, Brodick, Hedden, and Livingston separately, saying like for any n greater or equals to 0, there exists a complex curve in CP2 of degree 5 for n, that's genus 1, and a singular point whose link is T5 for n minus 2 and for 5 for n plus 2 torus knot. So here, this phi is a Fibonacci sequence starting from 0. So phi 0 is 0, phi 1 is 1, and phi n is the sum of the previous two zetas. So this is the Fibonacci sequence. And what they show is like they prove like there exists a complex curve of genus 1. And there's only one singular point where the link of the singularity is the torus link, phi 4m minus 4, and phi 4m minus 2, and a phi 4m plus 2. And also you can just you can construct the degree of this curve is phi 4m. So this genus 1 curves satisfy this link of singularities satisfied. Now we are asking whether we can trade this genus by a double points, either positive double points or negative double points by using our obstruction. So we find in a joint work with Mache and Ian, we find like we cannot trade the genus for a negative double points. The way we find this obstruction is what we used by this RKD is greater or equals to K, if I remember the obstructions clearly. Sorry. Yeah. And we just need to find the suitable values for small k, and we just to check this inequality does not satisfy. That's why we conclude like we cannot trade the genus by a negative double points. However, I would like to emphasize like we don't know whether we can trade the genus for a positive double points because the obstruction we provide pass through this case. So we cannot distinguish whether there's another stronger obstructions or is this always can be traded by the positive double points. Another example is also also provided by Brodick, Hedden, and Livingston. They prove like there are no non-obstructions for the existence of a curve of degree 7, that's genus 1, and the singularity link is T1073. And also there exists no obstructions for the curve with degree 33, and the singular point is T1291. So we don't know whether such curve exists. This is genus 1 curve plus the singularity is T1073 or T1291. So we don't know whether such curve exists or not, because I think their obstruction also pass through, so they cannot find. So it's not enough to say the curve exists or not. However, if we use our obstructions for double points, either positive double points or negative double points, we can still say something. We say like if such curve exists, then the genus cannot be traded for a positive double points. And the way we prove like is using the obstruction we provide in the previous notes of R of KD smaller or equals to the big K. And we find like there are some suitable values for the small k such that this inequality does not satisfy. And in that case, we just say like this curve, surely if it exists, then the genus cannot be traded by the positive double points. However, the problem is like we don't know whether such curve exists or not. So this is two examples we had for trading genus of double points. I think there are also some other questions one can ask. Is trying to find the restrictions of degree and genus if we have T2 and link of singularity. So this is also a very classical problem people have considered, saying like you restrict your singular points to be the particular type T2 and torus link. Then what is the restrictions for the topological data, like the degree of and genus of the curve? And our abstraction can also help say something. So we'll leave the proof of the main theorem and the more general settings in the second part of the video. Thank you very much for everyone's listening.